Okay, we want to now venture out of the world of first order equations and into the world of second order equations. Now, first order equations are hard already, and as you can imagine, when you pass to the second order differential equation world, things get even more difficult. So, we are very quickly going to narrow our focus, narrow our scope on a particularly tractable set of differential equations, namely the linear ones. Now, the linear differential equations, and I'll write down what those are going to have this very nice property around their solutions, which are going to make it possible for us to begin to think about these things in interesting ways. But even there, if we don't further narrow our scope, the theory is quite difficult. Okay, there are things that we can do. There's something called reduction of order, but I'm going to leave that as sort of extracurricular because we very quickly want to focus on an even narrower class of second order linear differential equations. Okay, um, and but fortunately, we're going to find ourselves in a kind of how to say, like a Goldilocks zone, in which we will be working with differential equations which are solvable and tractable to mere mortals such as you and I, but also at the same time, um, uh, very useful, very applicable. Okay, so let's get started here. Let's think about, like I said, second order linear differential equations, which is a lot of letters in a row to write, and I don't want to keep writing them, so I'll abbreviate this SOLDE. Okay. And the standard form for such a differential equation is something like y double prime plus p of x y prime plus q of x is equal to f of x. So as usual, p, q, and f are functions of x only. They are the coefficients of my second order linear differential equation written in standard form. Again, this is the standard form. Your second order linear differential equations might not always look like it, or might not always be presented to you in standard form. So you have to get it into standard form before you start applying the theory that we're going to be discussing when we discuss it. Okay. But yeah, this is the standard form, not unlike when we were discussing first order linear differential equations. We had a standard form there. Okay. Oh, and I messed up already. I don't know if you can detect where the mistake is, but I'm missing a y here. This should, of course, be a y. Okay, better. My bad. Okay, let's look. Well, no, actually, let me just throw a little bit of terminology at you, a little bit of vocabulary at you. We say this equation is homogeneous. This is the vocabulary word. If f of x is identically 0, is always 0 for all x. Okay? If f of x is the 0 function, so this thing over here on the right-hand side of the equation is 0, then we say it's a homogeneous equation. And it's non-homogeneous otherwise. Shocker, I know. We're going to use this word a lot. This is going to be very important for us because for reasons you'll see. Okay, so let's look at some examples before we go too far. Let's think about the following: y double prime plus k squared y equals 0. Then we can try to pattern match what we see in this example, second order linear differential equation, with the standard form. And what we observe, I hope, and what I hope you see, is that p of x, what's playing the role of p of x here, is 0. What's playing the role of q of x is k squared. and was playing the role of f of x. Oops, my bad. What the? Hello? What's playing the role of f of x is 0. So in particular, this is a homogeneous equation. It's a homogeneous second-order linear differential equation, okay? Okay, now why did I write k squared in this equation and not k? It's because I wanted to avoid having to write square roots of stuff. But not only that, the k squared signals to me that, in fact, this number here is non-negative. It's either 0 or positive, because anytime you square a constant, you always get something non-negative, yeah? And yeah, I should have maybe said this. K here is a constant. And that's not because constant is the first letter in KONSTANT, right? It's a constant number. It's a real number, okay? And that we're squaring it so it's non-negative. Okay, oops. So what are the solutions to this differential equation? Well, let's take y1 to be, how about, cosine of kx. So consider cosine of k times x. Well, what's y1 prime? Y1 prime, by the chain rule, is negative k sine kx. Hopefully that's straightforward. And clearly, y1 double prime is negative k squared cosine kx. So with this data, you can plug this information here into your differential equation. And what you're going to find is that it checks out. It satisfies it, right? Because y double prime is negative k squared kx, and k squared y is k squared cosine kx. So they kill each other, yeah? And you get 0. Great. But here's a point. What if I was to define y sub 2 to be equal to sine kx? Let's just track. What's y sub 2 prime? K times cosine kx. Y sub 2 double prime is k squared, no, with a negative sign. K squared, negative k squared sine kx. Yeah? And this again is a solution. Make sure you see that. When you plug in y2 into the differential equation, you again get, it again satisfies it. Okay, so point being, both y1 and y2 are solutions. Now, this isn't exactly a weird state of affairs, right? Back in the good old days of first-order linear differential equations, there we already saw that you can have infinitely many solutions to a differential equation, right? But typically there, what we saw is that now this is a little bit heavy. Typically there, we saw that there was kind of a one parameter family. Ooh, is that a weird word to say? A weird phrase? There's kind of an infinite family that is parameterized by a single constant. So, for example, just real quick, I'm going to erase this, but remember if we had something like the exponential growth equation, like y prime equals ky, the solution to this was y equals c times x of kt, right? Or kx. And here, the c is the sort of parameter, the one knob that we are allowed to turn and tune in order to get us a particular solution. This is the general solution here. And C is the sort of one knob, the one knob that we're allowed to turn in order to get a particular solution. Okay? So I'm going to say it like this. The solution space to this differential equation is kind of one-dimensional, the same one, because there's sort of one parameter that I'm allowed to tune. Here's what I want you to observe. So y1 and y2 here are solutions. But now, crucially, but so is any what's called linear combination. And I'll explain what this means in just a second. of y1 and y2. So in particular, if I define y to be equal to some constant c1 times the first solution, which we found to be cosine kx, plus some other constant c sub 2 times sine of kx. I claim, and I'm right, that this is again a solution to this differential equation. Do we need to check it? We can check it. Just real quick, what's y prime? This is negative c1k cosine. No, I messed up already. I really do know how to do calculus. Sine kx, okay, plus c2k cosine kx. Great. And then what's y2 double prime? It's it's negative c1k squared cosine kx plus c2k squared. Oh God, I messed up. Minus c2k squared sine kx. Great. Point being that this is equal to negative k squared y, negative k squared y. y2 double prime is negative k squared y. So now plug in y. Oh, why did I write y sub 2? I have no idea. It's late for me. Well, okay, so plug in this y into the original differential equation here. And you get exactly 0. You see that? If you add y, if you add k squared y to y double prime, because y double prime is negative k squared y, you get 0 when you add them together, yeah? So indeed, I was right. Both y1 and y2 are solutions, sure, but so is any linear combination of these, okay? And the feeling that I want you to feel is that now that we're in second order land, we now have 2 knobs that we're allowed to turn to generate solutions. We have C1, and now we have the second constant, C2. That's a 2-dimensional space. 2 knobs that we can turn, 2-dimensional space of solutions. Okay? With first order equations, linear equations, we had a 1-dimensional space. Okay? This is the feeling that you should feel. Do you feel it? Okay. Well, do we really have 2 dimensions here? Right? Because it could be the case, couldn't it? That these 2 solutions, this one here, this kx, cosine kx, and this sine kx, it could be that those 2 solutions are already constant multiples of one another. I mean, you probably have the sense that they're not, because you know cosine is sine, but phase shifted, right? And in particular, if you were to multiply cosine by some constant, you would just vertically you change what's called the amplitude of that sinusoidal wave. So it probably is not the case in particular. It's kind of ridiculous to allow ourselves to have this fancy, this fantasy that cosine kx is a constant multiple of sine kx, right? That seems wrong. But if it was, then what I described to you as being in fact a 2-dimensional solution space would in fact be 1-dimensional, because I could rewrite this sine kx here as some constant times cosine of kx. So this whole thing would just collapse into some constant times cosine kx. Do you see what I'm saying? So it's important to check that these 2 functions are not constant multiples of one another. Okay? They're not constant multiples of one another. Well, I just repeated myself. I noticed I don't know why I'm talking about this, but it just popped in my head, and I apparently have no ability to constrain my speech, even though this is entirely irrelevant to the class. But that act of repeating yourself, or repeating the end of your question, is something that I notice a lot of conservative talk radio hosts do. It's something that a lot of conservative talk radio hosts do. I love listening to those conservative talk radio hosts. So I've really picked up on their speech mannerisms. It's fantastic. Okay, anyway, and the next one we're going to talk about the idea of uh, when two functions are constant multiples of one another, and just lay out that set of ideas so that we can better understand what's happening in this. And then we're going to unify that with something, with another idea, which is crucial for the theory of second order linear differential equations. But I've already wasted your time in this video enough, so I'll stop this one. We'll do it, carry on in the second one.